Welcome to the Explainer. So, have you ever looked at a glass of flat soda or maybe just a sealed bottle of water sitting on your desk and thought that absolutely nothing is happening? It's a pretty common assumption. But beneath that calm, motionless surface, there is actually a chaotic, invisible frenzy taking place. Today, we're going to completely shatter the illusion of stillness and explore the totally fascinating world of chemical equilibrium. Here's a quick roadmap for this explainer. We'll start with the illusion of stillness, look at physical equilibrium in action, and see exactly why chemical reactions never actually sleep. Then we'll dive into the law of equilibrium, factor in pressure and gases, and wrap up with why all of this matters so much to our daily lives. Okay, let's dive right into this. Part 1. The illusion of stillness and the microscopic chaos underneath it all. I want you to consider this question for a second. What actually happens when a chemical reaction, quote-unquote, stops? Like when hemoglobin successfully binds to oxygen in your lungs, or when that soda on your kitchen counter finally loses all its fizz and goes completely flat. From our perspective, the human, macroscopic level, it looks like the system has hit the finish line, right? Process over. But if we could zoom all the way into the atomic level, we'd see a totally different reality. The reaction absolutely hasn't stopped at all. Instead, it's simply reached a state of dynamic equilibrium. This just means that the rate of the forward process perfectly equals the rate of the reverse process. And because these two opposing forces are happening at the exact same speed, there is zero measurable change in the overall concentrations. It's kind of a crazy paradox, honestly. You have this intense, rapid-fire, microscopic activity happening right at the boundary layer, while on the outside, everything looks completely perfectly still. Moving right along to Part 2, Physical Equilibrium in Action, featuring ice, soda, and closed systems. And this brilliantly illustrates the whole concept. Think about a perfectly sealed thermos flask filled with ice and water at exactly 0 degrees Celsius. If you check on it a few hours later, the amounts of ice and water haven't changed one bit. But here's the secret. Individual water molecules are continuously escaping the ice to become liquid, and liquid molecules are freezing right back onto the ice at the exact same rate. In a closed system like this, at a specific temperature, these physical states just lock into this dynamic balance. Whether it's liquid evaporating into vapor, solid sugar dissolving, or carbon dioxide gas dissolving into liquid soda, the vapor pressure, the dissolved solute, and the gas ratios all just balance out and stay totally constant. Now, if you're still having a bit of trouble visualizing this equal rate concept, think of this really cool water cylinder metaphor. Imagine two big glass cylinders. Cylinder 1 is completely full of colored water, and cylinder 2 is empty. Now grab two identical glass tubes. You use one tube to scoop water from cylinder 1 into 2, and simultaneously, you use the other tube to scoop water from cylinder 2 back into 1. At first, cylinder 2 fills up pretty quickly. But eventually, because your transfer tubes are the exact same size, the rate at which you move water back and forth completely equalizes. The water levels in both cylinders lock in and become perfectly constant, even though your hands are frantically scooping water back and forth. The overall volumes aren't changing, but the system itself? Super active. All right, part 3, chemical reactions never sleep, where we'll look at the Haber process and some cool isotopes. So we know physical systems balance out, but what about chemical reactions? Well, they do exactly the same thing. Consider the synthesis of ammonia. If we start with nitrogen and hydrogen gas in a closed vessel, they react to form ammonia. Initially, your reactant levels drop and your product level shoots up. But eventually, they just flatline. The concentrations become completely constant. But again, the reaction hasn't stopped. That ammonia is secretly breaking back down at the exact precise rate it's being formed. But how do we know for absolutely sure that the reaction isn't just stopping? Chemists actually proved this using a brilliant detective story involving isotopes. They ran the Haber process normally to get an equilibrium mixture containing regular ammonia, NH3. Then they ran the whole thing again, but this time using deuterium, which is just a heavier isotope of hydrogen, to get ND3. When they mixed these two equilibrated environments together and waited a bit, they checked it with a mass spectrometer, and the results were amazing. The atoms had completely scrambled. They didn't just find the original NH3 and ND3, they found mixed-up molecules like NH2D. If the reactions had actually stopped, there is no way that mixing would have occurred. This atomic scrambling is definitive, undeniable proof that chemical reactions in a closed system literally never sleep. Let's move on to part 4, the law of equilibrium, where math meets chemistry.
Back in 1864, these two Norwegian chemists, Goldberg and Waj, were studying these constants, and they actually formulated the law of mass action based on a generic balanced chemical equation. Just picture reactant A plus reactant B reversibly yielding product C plus product D. And those little lowercase letters you see, those just represent their stoichiometric coefficients, basically the number of molecules involved. From that simple setup, we derive this really beautiful formula. Kc, which is the equilibrium constant, equals the concentration of the products divided by the concentration of the reactants. And the really crucial part here is that each concentration is raised to the power of its specific stoichiometric coefficient. This constant, Kc, is a completely fixed number for a specific reaction at a specific temperature, no matter what amounts you actually started with. It is essentially the mathematical heartbeat of the reaction. And because we're dealing with pure math, there are some very logical rules when we manipulate the chemical equation. If you write the reaction in reverse, you simply invert the constant. It literally becomes 1 over Kc. And if you multiply the entire chemical equation by some factor, let's say n, the new equilibrium constant becomes your original Kc raised to the power of n. It's so cool how the math just perfectly mirrors the physical reality of the molecules. Part 5, Pressure and Gases, CAPE, and Adapting the Math.
Now, Kc is fantastic when you're dealing with concentrations in a liquid solution, which we measure in moles per liter. But for gaseous systems, trying to measure molar concentration is tough. Measuring partial pressures is way easier. So this brings us to a slight adaptation, CAPE. This focuses on the partial pressures of gases, usually measured in bars. But don't worry, both Kc and Kp are measuring the exact same dynamic balance. They're just bridged perfectly by the ideal gas law. So the crucial point to take away is this final conversion formula. Kp equals Kc times the product of R and T raised to the power of delta N. R is your standard gas constant, T is the temperature in Kelvin, and that delta N part is simply the difference in the number of moles of your gaseous products minus the moles of your gaseous reactants. Think about it. If a reaction produces the exact same number of gas moles as it consumes, delta N is 0, and anything to the power of 0 is 1, which means Kp perfectly equals Kc. Finally, Part 6, Why This Matters. Taking all of this from the lab straight to industry. Now, you might be wondering, why go through all this trouble just to calculate some invisible constant? Well, because understanding equilibrium is absolutely vital for human progress and survival. Seriously. By knowing this equilibrium constant, chemists can artificially tweak the conditions, like altering the temperature, pressure, or concentration to force the equilibrium to shift exactly where we want it. This is literally how we maximize the industrial yield of ammonia in the Haber process, creating enough fertilizer to feed billions of people. It's a real game changer. And it's also how we understand biology. That delicate equilibrium between oxygen and hemoglobin is what keeps us breathing and alive. On the flip side, a slightly different equilibrium involving carbon monoxide explains exactly why CO gas is so incredibly toxic to us. It finds to our blood and just won't easily let go, totally hijacking our internal balance. So as we've seen, equilibrium is definitely not a full stop. It is a beautifully delicate, dynamic dance of nature. We've learned how to measure it, calculate it, and even manipulate it to survive. So I'll leave you with this to ponder. As we face massive new challenges in medicine, energy, and the environment, how might humanity continue to harness these invisible laws of dynamic equilibrium to shape the physical world to our advantage? Thank you so much for joining me on this explainer, and remember, always keep questioning the stillness.